Okay, so we're going to start by thinking about our sine of an angle. So say I'm taking sine of some angle theta. Now, what we've been thinking about so far is however much we rotate, we get to that position, we draw our triangle, and we know sine is the opposite over hypotenuse. Okay, so that's what we're going to do. But now we want to think about the angle that we're rotating being a variable that could change over time. So think about the theta as being our x value, and then whatever the output is going to be our y value. If you think about like y equals mx plus b or y equals x squared. We're going to take all the values of sine and we're going to put them on an xy graph and see what happens. Okay, so just like normally, we can choose some x values and then find out what the y values are going to be. So we're going to choose some thetas and then see what the output, the y value is. So I'm picking these thetas from our unit circle. We could rotate 0 degrees. We could rotate 30 degrees, which is pi over 6. We could rotate 45 degrees, which is pi over 4. We could rotate 60 degrees, which is pi over 3. So because I can pick whatever x values I want, I'm going to pick those nice ones that I know my special right triangles for. We could rotate 90 degrees, which is pi over 2. We could rotate 120 degrees, which is 2 pi over 3. We could rotate 135 degrees, which is 3 pi over 4. I'm going to extend this one a little bit. We could rotate 150 degrees, which is 5 pi over 6. And we could rotate 180 degrees, which is pi radians. Okay, so that gets me through the first 180 degrees of the unit circle. Now I'm going to do the second 180 degrees. Okay, so my next rotations. I could rotate 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2. Everybody following where I'm getting these from? I know some of y'all don't have your degrees to radians memorized yet, but I'm just going 30, 45, 60, 90 in each quadrant, finding those values. Okay, next would be over 3. So it would be 5 pi over 3, 7 pi over 4, 11 pi over 6, and 2 pi. Okay? So then let's write down what these values would be. So if I rotated nowhere, sine of 0 puts me on the positive x-axis. That's the 0.10. I know sine is equal to the y value. So the y value there is 0. So when I rotate nowhere, sine of 0 is 0. Next, sine of 30. So 30 degrees is opposite 1, hypotenuse 2. And I'm in the first quadrant, so it's positive. Sine of 45 degrees. Opposite's radical 2, hypotenuse is 2. Sine of 60 degrees. Opposite is radical 3, hypotenuse is 2. And then sine of 90. So again, that's a special case. I'm up here. That is the 0.01. So my y value there is 1. So let's look at what's happening here so far. So we're at 0, then we jump up to a half. This is like 0.7 something. This is 0.8 something. And then this is 1. Okay, so the whole time we're steadily increasing. It starts off with a real big increase. After 30 degrees, we're halfway up to the top. But then it kind of slows down, right? And it keeps increasing, but the rate it increases slows down until it reaches its height at 1. And now then we're going to start going back down. So 2 pi over 3 is a 60-degree reference angle in the second quadrant, so it's positive. That would be radical 3 over 2. 3 pi over 4 is a 45-degree reference angle, again positive, so it is radical 2 over 2. 5 pi over 6 is a 30-degree reference angle, so it's a half. And then at pi, that's when we're back here, my y value is 0. So what do we notice as we fill out the first half of our chart? You see the pattern. We're slowly increasing, slowly decreasing until we drop off pretty drastically at the end. Okay, well then what happens when I go to the third quadrant? Now I'm in the third quadrant. Well, sine's going to be negative. So these values will be negative. And this is a 30-degree reference angle. So this is going to give me negative a half, negative radical 2 over 2, negative radical 3 over 2, negative 1. Then we start working our way back up in the fourth quadrant. Negative radical 3 over 2, negative radical 2 over 2, negative a half, and then back to 0. Okay, so I left this blank, but could we really keep rotating in either direction? I could pick the next one over here, or I could go backwards. I could have negative thetas as well and go in the other direction. But 2 pi puts me back here at 0. So the next value, the next y value again would give me 1/2. We start this whole thing over again and over and over and over in either direction. Right? It's all about the coterminal angles. Oh gosh, why did that not all tie together? I don't know. Let me see if I can do it real quick. Yeah, boy, I'm learning. Okay. No, why did that? You gotta be kidding me. Okay, let's just stay there. That's terrible. Okay, so now I'm going to graph this, and I'm making my own XY plane. Okay, so because all my thetas were positive, I'm going to focus like this is the origin right here. Okay? So let's think about what's the highest y value that my graph takes on. 1. What's the lowest y value my graph takes on? Negative 1. So this is going to go between 1 and negative 1. So I'm going to make this here my y value of 1. This here is negative 1. Okay, since this is the first time I'm drawing this graph, I'm going to try to make it as proportional as possible. So we know right here is a rotation of 0. So let's make right here a rotation of 2 pi, because we're going to use all of this here. So this is 2 pi. Halfway between them would be a rotation of pi, or 90 degrees. Okay, then halfway again, this would be pi over 2. And halfway here would give me 3 pi over 2. Everybody follow how I'm getting this? I'm halving. Okay, now if I halved pi over 2, this would give me pi over 4. So this is 2 pi over 4. The next one would be 3 pi over 4. 4 pi over 4. 5 pi over 4. 6 pi over 4, 7 pi over 4, 8 pi over 4. Okay, then to get to my pi over 6s, like, you don't have to put all these tick marks, but I'm going to put them for mine. And you can go back and watch this recording, because I know this is going to get pretty confusing if you don't have different colors. Okay, so I'm taking a fourth and I'm dividing it into 3 pieces. So that's basically like I'm dividing it into 12ths. This is pi over 12, 2 pi over 12, 3 pi over 12. Do we follow? 4 pi over 12, 5 pi over 12, 6 pi over 12. And the reason I'm doing that is because I need pi over 6 and pi over 3. So basically, this tick mark and this tick mark are not going to be used, because I'm going to go pi over 3, pi over 4, pi over 6, pi over 4, pi over 3. And so then this one and this one are useless. But again, I'm trying to keep it evenly spaced. Okay. And so let me just draw, right here's a half, and right here's negative a half. I really probably should put those numbers smaller. That's okay, I'll choose a different color. Okay, so when I plot my points, my first point is at 0, 0. X value is 0, Y value is 0. Next one, at pi over 6, I'm up to a half. So you see how that's grown a lot very quickly. Then at pi over 4, I'm radical 2 over 2. I told you you can put that in your calculator. It's about 0.707, I think. So I'm almost halfway here to 1, not quite. Then at pi over 3, I'm at radical 3 over 2, which is about 0.866. So I'm almost to 1, but I'm still not quite there. And then I got to go all the way over to pi over 2. I finally reach a value of 1. So this kind of grows pretty quickly, and then it kind of steadies off. Kind of like a square root function, or kind of like a parabola turned sideways, right? Same idea. And we could find every point in between. Just because we didn't find them doesn't mean they don't exist. We just picked the easy ones for us to do, which were our special right triangles. Now the next point is at 2 pi over 3. I need to be back to radical 3 over 2. So that's about right here. Then at 3 pi over 4, I need to be at radical 2 over 2, which is about 0.7, which is about there. At 5 pi over 6, I need to be down to a half, which is about right here. And then at pi, I'm at 0. So now if I graph that portion through, then you can really see that half of a parabola, right? But now it's going to do something different on the other side of it. So when I go to 7 pi over 6, I should be at negative a half. So my negative a half is here. This is my 7 pi over 6. It's this yellow one. So that's going to put me here. 5 pi over 4 is negative radical 2 over 2. 4 pi over 3 is negative radical 3 over 2. And then all the way to 3 pi over 2 is when I finally reach negative 1. So again, this quarter It's going to grow pretty quickly and then kind of level off until it reaches its lowest point right there. And then at 5 pi over 3, I'm at negative radical 3 over 2. So that'd be about right here. 7 pi over 4 is negative radical 2 over 2, so negative 0.7. 11 pi over 6 is negative 1/2, which puts me there. And then 2 pi puts me here. And so if I go one time all the way through my circle, one revolution, and I put it on an XY plane, this is what I come up with. Okay, does this remind anybody of anything that's used like in the real world? Huh? Radio waves, right? Any kind of X-ray, any kind of wave. That's what it comes from, is broadcasting out at a certain frequency. And so we're going to talk about different frequencies, different wavelengths, and how we can change them, because that's how radios change what wavelength their music goes out on, right? But like we said, let's think about this again. If I were to look at the next part of the wave, right, because this was just one revolution. If I went around again, which I know these X values are going to be wrong. Oh, no. There it goes. I know the X values are going to be wrong for the next part of my wave, but you see how this wave would just continue over and over and over and over, just like a sine wave would. Every revolution, I would get the same values again. It's going to keep bouncing between 1 and negative 1. It's never going to get any higher or any lower. And it's going to continue this in both directions forever. Instead of using all the points from the unit circle, we're going to focus on certain key points that will help us graph our sine curve. So just like we did when we did parent functions with parabolas, square roots, and we did the cube functions, we had certain key points that we memorized, and we just did the transformations from those points. And we know what it looks like in between. So our key points here, well, we need to know the beginning point, when it reaches its highest, when it has another x-intercept, when it reaches its lowest, and then when it completes one revolution. Those are our 5 key points. And we understand what the graph's going to do in between those key points. So right here, I'm going to go 0, 0 is the first key point. The next one is at pi over 2. We reach the height of 1. Then when we get back to pi, we get back to 0. Then 3 pi over 2 gives us the low point of negative 1. And then 2 pi completes a revolution. It gets me back where I started. So for a sine graph, let me reiterate that. This is for sine of theta, y equals sine of theta. This is our 5 key points. So right here, when they use their graphing calculator, they set the window to be between 0 and 2 pi, which means the lowest value that we could see was 0, and the highest value we could see is 2 pi. In the next picture, they have changed that window. Now they have widened that out. So like right here, 0. When it completes one revolution, that's back to here. That would be 2 pi. And then we see one more revolution. So this will be all the way to 4 pi here. And then we go backwards and we see a revolution. So that puts me at negative 2 pi here. So in this window, we're looking at the values from negative 2 pi up to 4 pi. And we could keep widening it, and we would just keep seeing more of these sine waves, because it's the same pattern over and over and over. Okay, so this is going to give us a new term to call this sine wave, It is called a periodic function. If y is equal to f of x is a function and alpha is some non-zero constant such that y equals f of x plus a, okay, so that's very fancy, it's called a periodic function. So let's think about what this is saying. This is saying if there exists a number that I can add to the x values and it gives me the same y value over and over, then this is called a periodic function. So with sine, what is that alpha? What could I add to every x value that would get me to the exact same y value? In the unit circle, what is our number that makes things repeat and we get the same thing back that we started with? Think about our coterminal angles. When we added 2 pi, we got the same initial and terminal side. So with sine and with cosine, if we add 2 pi to the x values, we will still get the same y value. So in this specific example, our alpha could be 2 pi, could be 4 pi, 6 pi, 8 pi. There's a whole bunch of different things I could add that would not change the y value, right? Because 2 pi is a full revolution, gets me back where I started. Good. Okay. So that's the big fancy definition. That's why we can call it a periodic function. The smallest such positive constant alpha is the period of the function. So we talked about that alpha. We could add 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. There's a bunch of alphas we could add that would put us back where we started. The smallest one we can come up with is called the period. Okay, so a period is how long it takes for the pattern to repeat itself. So with sine, our period is 2 pi because we start back over every 2 pi. We get back where we started. So we would call 2 pi the period of the function of the sine function. Okay, so we're going to go ahead and start looking at transformations. It says use the table to the right to graph the function y equals 2 sine x. So my parent function is y equals sine x. So what's different between y equals sine x and y equals 2 sine x? Just like we spotted before in 112. The difference is the 2 out front. What's the 2 doing? It's multiplying. So when we're multiplying, we are stretching the graph, just like we did before. I'm multiplying sine by 2. That's going to change all of the y values by 2. So when it used to be 0, 0, that one's still 0, 0. It used to be pi over 2, 1. But when I stretch it by 2, now it's pi over 2, 2. Pi 0 won't change. 3 pi over 2, this should be a negative 2 here. That's a misprint. And then at 2 pi, we should be 0. So again, right here, the dark one, this is my normal parent function, y equals sine x. And then this is what happens when I stretch the graph. So the heights get higher and the valleys get lower, right? But the x-intercepts don't change. By 2. So we're stretching the graph. In the graph, notice this changed the original sine curve by multiplying all the y values by 2. In Math 112, we called this stretching the graph vertically. Well, it's going to be called something different. Everything that we used to call it stretching, compressing. We called it, now the shifts are going to be the same. Okay, but our stretches and compressions are going to have different names. Okay, so when we stretch the graph or shrink the graph now, we're going to call that an amplitude change. Okay, so if you think about amplitude, think about sound waves. If you're turning the volume up, your sound waves are getting higher and lower. It's got more bounce back and forth. So that is an amplitude change. We can find the amplitude of any graph by taking the maximum y value, subtracting the minimum y value, and dividing by 2. Notice that it's in absolute values, so that means amplitude is always positive. We cannot have a negative amplitude. So it's always the positive number there. You can think about the amplitude as the distance from the center of the wave to the crest or trough of the wave. So like on our example here, now then we reach a height of 2 and we reach a depth of -2. So if I plugged into the amplitude formula, my maximum y value is 2 minus my minimum y value, which is -2, and then we divide by 2. We're basically finding the average is what the dividing by 2 is. You're taking the highest, the lowest, and then you're finding the average. So that's going to give me 4 over 2, which is 2. So 2 being the amplitude means from the center of the wave up to the highest portion would be 2, and from the center of the wave to the lowest portion would be a count of 2. That's what the amplitude shows us. So what would be the amplitude of our normal sine function? The one that bounces between 1 and -1. Okay, we could think the highest y value is 1 minus the lowest y value is -1 divided by 2. So that's 2 over 2, which is 1. So by default, our sine wave has an amplitude of 1. It bounces up to a height of 1, down to a height of -1. So from that center, it goes up 1, down 1. And that's how we describe the amplitude. Okay, here's the next one. As we have seen, we can take the unit circle and create the cosine curve. So what we've looked at so far is a sine wave. We could do the same thing with a cosine wave. Yes. I could go through and create it again, but that'd be another 17 minutes. But it's the exact same process. We pick the x's, find out what the y's are. The difference is they look very similar, but this one starts at a different place. The sine wave starts at the origin of 0, but cosine wave would start at 1. Right? The starting point's different, but it does the same process. So the key points for a cosine wave would be 0, 1, pi over 2, 0, pi -1, 3 pi over 2, 0, and 2 pi completes my revolution, gets me back to 1. And that process would start over again. So again, those 5 critical points, we're picking the highest points, the lowest points, and the x-intercepts to be our key points. Now it's got a question. What is the period of the cosine wave? How long did it take cosine to repeat itself? It would be 2 pi again. When it gets to 2 pi, we start back over from where we began. Okay, now it tells me to look at this. We have graphed cosine. Cosine of x is the darker graph, the one here in blue. And now we have multiplied, in the last example we multiplied by 2. This time what have I done? I've multiplied by -3. So what is that going to do, multiplying by -3? Well, the 3 is going to change the amplitude, just like the 2 did. So now the cosine graph is going to have an amplitude of 3. That means from the top to the center is 3, and from the center to the bottom is 3. But what else happened to my graph? Where I used to reach a mountaintop, it's now a valley. And where there used to be a valley, it's now a mountaintop. Because this negative reflected the graph. Just like a negative reflected the graph in 112 with the parent functions. Same idea. So when we multiply by negative, it's going to change the sign of all of my y values. And then this 3 is going to stretch the graph or change the amplitude of that graph. So how does it compare? It's stretched by 3. And we're going to call that an amplitude change. And then it's also reflected over x-axis. That does not look like axis. There we go. In section 2.3, we discussed transformations and how they affect a parent function. So how is the graph of the function y equals 3 radical x different from the graph of the function y equals radical x? Well, that's where we talked about before. This is a stretch by 3 of the graph. So we're multiplying all the y values by 3. In Math 113, this has a specific name when we deal with a trig function called amplitude. The amplitude of y equals a sine x or y equals a cosine x is the absolute value of a. So we can always identify the amplitude by looking at the number that's being multiplied out in front of sine. So if I was given the graph and finding the amplitude, that's when we would use the formula that we looked at before. High point minus low point, and then divide by 2. So finding the average when I'm looking at a graph will give me the amplitude. But if I'm given a function like this, I can identify the amplitude just by looking at the number that's being multiplied by sine or cosine. So in example A, y equals 5 cosine of x, that means the amplitude here would be 5. Okay, then in B part, sine is being multiplied by negative 2/3. So my amplitude here would be 2/3. Remember, amplitude is always positive. The negative is a reflection. So amplitude is the absolute value of A here. So that means my amplitude is always a positive number. So what do you think this 2/3 is going to do? When we multiply by 2, 3, and 4, we're stretching the graph. When I multiply by a fraction, a number less than 1, I'm going to compress the graph. I'm going to make the amplitude smaller. The next thing, this will be the last thing we get to. In Math 112, we talked about horizontal transformations of a function y equals absolute value, or y equals the square root of x by adding or subtracting a c to the x value. So for example, y equals the square root of x minus 2. So what was happening here? We were subtracting 2 on the inside of the function. So this moved the graph right 2 units. Remember, on the inside, it always moves it opposite the way it looks like it should. So subtracting 2 is going to move the graph right 2. If I add 5 on the inside, that's going to move the graph left 5 from its original position. We have the same thing in 113. It's called a phase shift. So where before we called them horizontal transformations, shifts left or right, now we call that a phase shift. A phase shift of a graph y equals sine x minus c or y equals cosine x minus c is c. So phase shifts can be positive or negative. So when I look here, what is the phase shift of the function y equals sine of x minus pi over 6? So because this is going to move the graph right pi over 6, my phase shift is going to be pi over 6 because it's moving it to the right in the positive direction. Now for the next one, when I'm looking at cosine of x plus pi over 3, that's going to shift the graph left pi over 3. So we would say the phase shift here is negative pi over 3 because it went left. And now we're going to be looking at vertical shifts. So a phase shift was being added or subtracted inside the function. That's how you knew it messed with the x values left and right. Right here, this is outside of the function. Here's sine of x minus 6 and cosine of x plus 2. So those are going to be our vertical shifts up and down. And these work the way they look like they should. So right here, if I'm subtracting 6, that means my vertical shift is going to be negative 6, which is going to move the graph down 6. If I look at y equals cosine of x plus 2, that's going to give me a vertical shift of 2. It's going to move the graph up 2. The last transformation we're going to do is a period change. So what this is really doing is it's going to be a horizontal compression or a horizontal stretch is what it's going to look like. But what happens is we know the period of our sine wave on its own is 2 pi because the period is how long it takes for the graph to repeat itself. So to start with, the sine wave defaults to a period of 2 pi. But that period can change. So right here, if I have y equals sine times, or sine of b times x, or y equals cosine of b times x. So see, there's going to be a number being multiplied on the inside. As long as the b is greater than 0, it's given by this formula. The period is 2 pi divided by b. So this is the default period of sine and cosine, and then divided by the number that's being multiplied. So it's still kind of like doing the opposite. Right here when we were multiplying by, like right here we're multiplying by 4. Okay, so if I want to find the new period of this graph, I know that the period defaults to 2 pi. That's what it is without any transformations at all. But because it was being multiplied by 4 on the inside, we have to divide that period by 4 to find the new period. And then we simplify. 2 over 4 is a half. So I could say the period of this function would be 1/2 pi or pi over 2. Okay, I'm going to look at C next. Okay, so I've got y equals cosine of x divided by 3. Okay, well, we don't really talk about it, a number being divided on the inside. So the way we want to think about this is think about this as cosine of 1/3 times x. Because dividing by 3 is the same thing as multiplying by 1/3. So now if I wanted to find the new period, I could say that the period used to be 2 pi. That's what it defaults to. But now I need to divide that by 1/3. So again, you could use your calculator. I would multiply by the reciprocal. And so that's going to give me 6 pi. So the new period of this graph is going to be 6 pi. And we'll talk about how we do that with each individual point, but that's not really what this first homework is on, so I don't want to waste time doing it now. Okay, then the B part, now x is being multiplied by pi over 2. So my original period was 2 pi, but that's being multiplied by pi over 2, so I need to divide by pi over 2. Now this time, this is the only example we've had where the number that was being multiplied has a pi in it. So that means my pi's are going to cancel when I work this out. So I've got 2 pi over 1 multiplied by the reciprocal. These pi's cancel, and I've got 2 times 2, which is 4. So you can have a period that does not include pi, and when that happens, we would change our x values on our x-axis. We wouldn't have to go in terms of pi anymore. We would just use regular old numbers, 1, 2, 3, 4, and so on. If I read, it says if the function is y equals sine of 2x, the period is equal to pi. So you could actually fit 2 cycles of the graph y equals sine of 2x in a normal period sine of 2 pi. So kind of what the period change does, if this is my normal sine wave, that's 1 full period, 1 revolution. When I change it to a period of pi, then that means halfway through it's going to have already finished 1 cycle. It's going to look like that. When you change the period, you're making those waves happen more frequently or less frequently. So when the period decreases, that means the waves are happening more frequently. And like I said, we'll focus more on graphing the points in a second, but we want to be able to make sure we know what's happening in each situation first. The general sine or cosine wave. The graph of y equals a times sine of b times x minus c plus d, or the same for cosine, is a sine wave. The a on the outside changes the amplitude. The period is going to be 2 pi over b. The phase shift is going to go right or left c. It's going to be opposite signed, and then it's going to go up or down d for a vertical shift. So it tells me to sketch one cycle using the new period. So this is the order we do them in. We first find the period, then find the amplitude, then shift the graph left or right, then shift the graph up or down. If you don't do them in that order, you could mess them up. So again, you have to make sure the things that are being multiplied are adjusted first, then the things being added or subtracted are adjusted last. Kind of like your normal order of operations. Identify where all of these transformations are coming from. So like if I look at A, y equals 3 sine of 2 times x minus pi over 2 minus 4. The first thing I want to do is find the period. Okay, so I know for a sine wave, the period defaults to 2 pi. But now that x on the inside is being multiplied by 2. So to find the new period, I have to divide by that 2. 2 divided by 2 is going to give me a period of pi radians. Next, I'm going to find the amplitude. The amplitude is the absolute value of the number being multiplied on the outside. So that would be an amplitude of 3. Next, we find the phase shift. That's what shifts the graph left or right. I look here, we are subtracting pi over 2 on the inside of the function. So that's going to shift the graph right pi over 2. So it's going to be a phase shift of positive pi over 2, which means we're going right pi over 2. And then we have a vertical shift. On the outside here, it's minus 4. So we're going to shift the graph down 4. Okay, look at the next one for 2 cosine of 3 times x plus pi over 3 plus 1. So first thing I want to do is find my new period. Cosine has a period of 2 pi by default. But now on the inside it's being multiplied by 3, so I'm going to divide by 3, which means my new period is 2 pi over 3. Next, I would find the amplitude. The amplitude is the number that's being multiplied on the outside, which is 2. Okay, next we'll find the phase shift, shifting the graph left or right. So we are adding pi over 3 on the inside. So that's going to shift the graph left pi over 3. So it's going to be negative pi over 3. And the vertical shift plus 1, that's going to go up 1. Okay, let's look at C. So first thing I want to do is I want to see if the period has changed. So it's a sine function, so the period defaults to 2 pi. We're going to divide by anything that's being multiplied on the inside. So it's being multiplied by 5 pi. So I'm going to divide by 5 pi. So now my pi's cancel and leaves me with just 2/5. So the period of that function would be 2 over 5. Okay, next I'm going to find the amplitude. Now the amplitude can never be none. Okay, so we find the amplitude by seeing what number is being multiplied out in front. Well, there is no number, but the amplitude then is just the default amplitude, which is 1. Remember, that negative out there is just a reflection of the graph. It doesn't change the amplitude. It's just going to change where the valleys and the peaks are. They're going to be in the opposite places. But the amplitude is still 1. So I'm just telling you now, the amplitude can never be none. Just because the amplitude doesn't change, that doesn't mean the amplitude is none. Okay? Then we find the phase shift, which is shifting the graph left or right. So we are adding 2 on the inside. So that's going to be a -2 phase shift. We're going to go left 2. And then I've got this -3 on the outside. That's going to be a vertical shift down 3. So we put -3. Okay, D is a little interesting. So I've got -3 times cosine of 2x minus 4 pi minus 1. So now my phase shift is going to be a little out of whack because this 2 is not outside, like being distributed to both units. So there's a couple ways you could do it. What I found is, because it's not factored out to start with, let's go ahead and factor it out at the beginning. I think students seem to like that better. So this is going to be -3 cosine of, now I'm going to factor that 2 out in front. So it's cosine of 2 times, that's going to be x minus 2 pi. And then you've got the -1 still on the outside. So again, we're just factoring the 2 out of everything that's in parentheses. Don't factor it out of this 1 here. So now when it's in the general form like all the other ones, we can find the period. Because it's cosine, it defaults to 2 pi, but it's being multiplied by 2. So we divide by 2, which means my new period is going to be pi. Next, we find the amplitude. It's the absolute value of the number being multiplied out front. So it's a -3, so the amplitude is 3. Okay, phase shift. So this is where we have to look at the new factored form. Right here, what's inside, we're subtracting 2 pi. So that's going to shift the graph right 2 pi. And again, that's going to be to the right. That's why we make it positive. And then lastly, we have our vertical shift, up or down. We have a -1, so that's going to shift the graph down 1.